Hi, I'm Chris. In my last video, I went through the process of how I wrote a module to multiply two significands as part of the code to multiply two floating point numbers using Verilog. In that video, I left you with three study questions. The first question was about adding the final partial product. This is the statement which adds the final partial product to get the product of our input values A and B. The first question was, why is it safe to replace the statement above with the following statement? After examining the two statements, you should see that apart from formatting, the only difference between the two statements is the second argument being passed to the adder module. That is, the first statement creates a mask from the most significant bit of the input value B and creates the final partial product by ANDing the input value A with that mask. The second statement doesn't bother to create the mask and simply passes in the value A without any additional processing. In this context, why do these two statements give the same result? If you watch the video which explains how the IEEE floating point formats work, you may remember that when we store a normal value in the IEEE floating point format, that the stored bits don't form the whole of the significand value. For normal numbers, there is an implied leading 1 bit which doesn't get stored. So, when I extract the significand field of a normal number, I automatically prepend a 1 bit. For subnormal numbers, there is no implied leading bit, but when I extract the significand for subnormal numbers, I left shift the subnormal significand so that the first 1 bit in the significand gets shifted into the most significant bit location, that is, into bit nsig. The Verilog code for the floating point multiply operation only uses the output of the significand multiplicand circuit in the case that the input values A and B are normal numbers or subnormal numbers, so we are guaranteed that the most significant bits of A and B are both 1. Since 1 times A is just A, the last partial product will always be A, and there is no need to compute the partial product using a mask. The next question was, what advantage does this version of instantiating the adder module have? In theory, it saves a few gates. This potentially makes the design smaller, which saves resources. With fewer resources consumed, there could be some benefit of packing the resources we do use closer together, keeping the path lengths shorter, and shorter path lengths tend to run faster than longer path lengths. The final question was, what implications does this code change have for our testing procedures? For the half precision IEEE floating point format, A and B are each going to be 11 bits wide. This means that there are 2048 possible values which can be stored in each A and B. In hexadecimal, these 2048 values range from 000 to 7FF. If we exhaustively test all possible values of A and B to verify that the multiply circuit works in all cases, then the number of tests we need to perform is over 4 million cases. But we know that the most significant bits of both A and B are 1. So the actual number of possible A and B values is 1024. This reduces the set of values we need to test to the range of 400 to 7FF hexadecimal. This reduces the number of cases to exhaustively test our multiply circuit by a factor of 4 to about 1 million test cases. Now, before going on to make improvements to the significand multiply module, I'd like to ask you to subscribe to my channel, click like, and pass along word of this channel to interested friends and colleagues. Up to this point, all of the Verilog code which I've written has been parameterized, so that it's easy to simply recompile the code with new values for the number of bits in the exponent field, NEXP, and the number of bits in the significand field, nsig, so that the Verilog code will support the IEEE 16, 32, 64, and 128-bit binary formats. In this video, I'm going to write a faster version of the significand multiplication module, which is specific to the 16-bit binary floating point format. Similar routines could and should be written for the other binary formats. Let's look at the data flow through the current sigmul module. As this diagram illustrates, we start by adding the first and second partial products. Then to that subtotal, we add the third partial product, followed by the fourth partial product, etc., until all 11 partial products have been summed. The additions all happen sequentially. Let's call the time it takes to perform a single addition t sub add. Then the total time to perform this multiplication is about 10 times t sub add. When writing software, one is often forced to perform tasks sequentially. And even though Verilog is a programming language, the output is a circuit design, and in our circuit we can often perform tasks in parallel. For example, if we pre-compute all of the partial products, we can perform 5 additions in parallel. That is, while we're adding partial products P0 and P1, we can simultaneously be adding P2 and P3, P4 and P5, P6 and P7, and finally P8 and P9. Similarly, we can add the outputs of this first stage in parallel. Again, since we're performing these additions in parallel, this stage takes about t sub add time to perform. Our next stage takes an additional t sub add time, as does our final stage. This reduces the time needed to perform 10 additions to a total of 4 times t sub add. That is, we can expect that adding the partial products in parallel takes about 60% less time compared with adding them sequentially. Of course, we'll have to confirm these numbers when we actually program an FPGA, but things are looking good. What else can we do to improve performance? In the previous video, I created a simple ripple carry adder. Ripple carry adders don't require many logic gates. They're easy to build and easy to understand, but they're not very fast. This is because it takes time for the carry to ripple through the adder. In this video, I'm going to implement a carry look-ahead adder. It's faster than a ripple carry adder. Carry look-ahead adders are typically implemented to add fixed-width blocks, such as blocks which are 4 bits wide. Some of the additions in this adder will be for add-ins, which have widths which are not an even multiple of 4. Because of this, I'm going to parameterize the module so it can be used to handle blocks of 2 and 3 bits also. In the case of a leftover block which is only 1 bit wide, I'll simply use a half or full adder. Here's my implementation of a carry look-ahead adder module written in Verilog. Information about how carry look-ahead adders work can be found in the book Digital Design and Computer Architecture, 2nd edition, by David Money Harris and Sarah L. Harris. Let's look at how we add a pair of partial products. As you can see, we're adding two 11-bit partial products. But remember that we need to shift the second partial product to the left by 1 bit position. When we sum bits A10 and B10, we could get a carry out which would get added to bit B11, which in turn could lead to a carry out, so we need to leave room in the sum for bit S12. This means that in the bit vector which holds our sum, we need to have room for 13 bits. Using the carry look-ahead module, how many times do we need to instantiate the module? To begin, notice that bit A0 never needs to go into an adder because it is the only bit which contributes to the output bit S0. We can simply copy A0 into S0. Each carry look-ahead module can take up to 2 4-bit inputs and a carry-in bit. The module to add 2 of the original 11 partial products might look like this. The final instantiation of the carry look-ahead module requires that I left pad A with an additional 0 bit. Also note that for the last instantiation of the carry lookahead module, I can pass the 13th bit of S to capture the carry out. That way, I only need to instantiate a 3-bit adder. This will save me a few gates and their associated delays. Before moving on, note the name of this module, A11 by 2. By adding two partial products, this module generates the product of the 11-bit input value A and a 2-bit slice of the input value B. That is, the name signifies that we're computing the product of an 11-bit value with a 2-bit value. Then to add the output from two instantiations of module A11 by 2, I need the module A11 by 4. Note that the two least significant bits of A have no corresponding bits in B, so these two bits can be copied directly into the result. Likewise, B has two most significant bits which have no corresponding bits in A. However, we can't just copy these bits into the result. They can be affected by the carry bits which come from less significant columns. Because of this, in the third instantiation of the carry lookahead adder module, I needed to left pad the most significant slice of A with zeros. Then I need to pass the carry out bit from that instantiation into a half adder to calculate the most significant bit of our sum. Similar to the previous addition module, this name signifies that it produces a product of A with a 4-bit wide slice of B. There will be two of the products of 4-bit slices of B. The module A11 by 8 adds them to get the product of A and the least significant 8 bits of B. Again, note that the 4 least significant bits of A have no corresponding bits in B, so we can copy these bits directly into the sum. Similarly, the input value A needs to be left padded with zeros so we can compute the most significant bits of our sum. We have one product of A and a 2-bit slice of B left over. The module A11 by 3 adds that product with the partial product of A and the most significant bit of B. This is the code for the module A11 by 3. The module A11 by 11 adds this sum to the output of A11 by 8 to complete the calculation of the product of the two input significands. Here is the code for A11 by 11. Finally, here is the sigmul_10 module, which controls the instantiation of all the other modules. Don't be deceived by this module. The modules which this code instantiates are being executed in parallel, even though it looks like it's performing tasks sequentially to software engineers such as myself. This can be confirmed by looking at the schematic. In summary, I reworked the 11-bit integer multiplication circuit to perform much of the work in parallel. I sped up the addition algorithm, and the next video will do even more to optimize the circuit. Please share this video with friends and colleagues which might have an interest in this video series. Questions and comments are always welcome. If you found this video useful, please click like below. While you're at it, subscribe to the channel, then click the bell to be notified when new videos are available. Thanks.